a 7-sided figure. If a 360-degree circle is divided into 7 equal segments, then the degree between each of the points will be 51.42, 360 divided by 7. And half of that will be 25.46, so you get a 14-sided figure if you divide the circle by 25.46 degrees. That's going to have a bearing on the ratios of these distances in these Greek spirals, in this band of Greek spirals. But before we get to the ratio, what does it mean? What's it about? Well, the spiral is compressed. It's squeezed into this band, so it's under some form of compression. And each spiral is inverse to the one next to it. And now, when spirals are inverse to each other, one could safely assume different directions in the current. So we're looking for bands of compressed spirals that are inverse to each other. This is Jupiter. That is the moon Europa in the foreground. And this obviously is the great red spot. Now, if I put a pair of spirals on there, you can see that it doesn't match that shape. And we're looking directly at the great red spot. They're just not compatible at all. But if I compress the spiral vertically, then the curvature does match what's happening in there. And that is a vortex. It's an ingoing vortex. It's moving in anti-clockwise. But all around it, there are clockwise spirals. There's a clockwise spiral here. There's a clockwise spiral here. But an anti-clockwise spiral there. And what would it be that compresses the spiral? And the answer is, I believe, the counter-rotating bands that occur over the sphere of Jupiter. Saturn's got the same thing. And within those bands, there are vortexes, spirals, storms, whirlpools, arranged in circles. And the counter-rotating nature of the vortexes is perhaps due to the interaction between the counter-rotating. This is from an infrared flyby over the pole of Jupiter. And we can see there's a ring of vortexes encircling the pole. There's 8 vortexes there. And they appear to have some kind of symmetry. So they'll be arranged at every 45 degrees. They're all going the same way. They're all anti-clockwise. And that might be because there's no strong counter-rotating band just out here. Or it might be just because they're in this electromagnetic hemisphere that they're all rotating the same way, or shaped in the same rotational direction. But in the center, there's another vortex here. And that's a point in the crop circles. If you are looking at a circle and in the grass there is a twirled spiral, it may well mean that you're looking directly down on the pole and the circle around it will be on the equatorial plane. Whereas if there isn't a spiral carved into the grass at the center of the circle, it's more likely that you're looking at a sphere side on, so that you won't see the polar spiral. But what about the ratios in the 7 split crop circle we're examining? If the crop circle had 8 splits, the ratio would be 0.8538. So we need to calculate what the ratio is for a 7 split figure. What I have here is a 7-sided figure, but it's not a polygon. It's actually comprised of spirals, which are arranged in motifs, which in turn are a pair of reflected spirals, like so. So that motif is then repeated at every 51.42 degrees, which is 360 degrees, divided by 7. Now, if I wanted to split this distance by 25.46 degrees, which is half of 51.42, I would then get a 14-sided figure. And if I halve the 25.46 to 12.73, I would then have a 28-sided figure. So what we're going to do is we're going to zoom in to an area just about here. Okay, and let me see our bold line here. I'll take that out. Take that out, there's spiral there. Take that out. Now, this outside red circle here, if I reduce that by, well, let's say 90, it doesn't hit these intersection points that are created by the spirals, which in this case, incidentally, are the 0.729 rate of decay over 90 degree spirals. So that would be 729 there. That's those ones. And it has a closing rate of 2824, and when there's 2 of them, it goes to the square root, which is 531441. Anyway, this doesn't hit this point here, so a little bit of trial and error, and then eventually establish that the correct reduction to that line was 91.34%. Well, 9133. I've got a 9133. It might be, yeah, and now it hits right on the intersection points there. And it will continue to do that towards the center. And that's how I can check that it's at least reading reasonably accurately. If it stays on register to those X points, then it's the ratio, according to the spirals, that you will find if you split the circle by 7, Now, if I take the 7-sided figure and rotate that by 25.46 degrees, then the new X points generated by that fall at the logarithmic halfway distance between this line and this line, and therefore go to the square root of 9133, which is 95.57. And if I decided to cut that one finer to half of 25.56, which is 12.73, then the ratio will drop to the square root of 9557, which is 9775. And if I take the outside circle and I reduce that towards the center at 53.1441, which is the square root of the closing rate of the 0.729 decay over 90-degree logarithmic spiral, otherwise known as the 2824 closing rate, which then splits to 531141, it's always going to land on that intersection point there at 531441. So it doesn't matter how many times the circle is split into 7, 13, 21-sided figures. It's always going to have 531441 as a ratio. And what happens is that if the circle is split by 7, there will be 7 equal reductions between 1 and 531441. That 5299 there is 531441. There's just a problem with maybe an extra decimal point up here or somewhere. But it's still close enough, even with a calculator of this simplistic format, to point us in the direction of what the ratios are over various polygons and crop circles. But now it's a matter of seeing whether or not the ratios presented in the crop circles for 7-sided figures agrees with this. Well, just to give you an idea of the geometry, take the pen tool and put that line there in, and I'm going to rotate that by 25.46. Which gives me this angle here. And I'm also going to rotate it 12.73. Which will give me the split down the axis of those two through there. That's actually 51.42 degrees there, and that's 25.46. And there's a bit to analyze there and what that is, but let's have a look at the ratio. There's 2 circles I've left off. One is here and the other one is here. But we'll go in for a closer look. Here. So this drop from there to there is 9557, as is this one, and then that is 9775, then 9557, then another 9557. So what happens then is that 95.57 doesn't quite get to the edge of that circle, so I'll give it another 9775. Oh, there we are. Okay. So there's that circle, and now I want this one, and that drop there is this one, 4840, twice. So it's the square of 4840. There's one. I'll just give it another one. There's two. Oh. And moving it up, that's just about perspective. But there it is there. So that's that ratio. And it's good because it means that it's accurate from the 2824 spiral calculator. And we can apply it, the same calculator, to any ratio that the crop circles might have. And in the meantime, on the subject of 7 split ratio, there has been another crop circle with 7 points, and this is it. It's the only one I know of. From the outside circle there, it's a robust 9133. And from the outside circle, it's 7617. For these inner circles. Like so. And I think these are supposed to go through these apexes up there, somewhere about there, from the square root of the difference, 9557. But apart from seeing the ratio in there, I don't really know what it means. I can't link it to anything. But still, definitely 7-point ratio.